Hello, students. Because this is a very big section, there's a lot of material here. Probably the last thing we should do is change the subjects and start talking about groups. But I think since some of you have had exposure to groups, and since you might already be familiar with quotient groups, it might help you when things come to quotient vector spaces. So how do quotient groups work? Let's just refresh our memory a little bit. You have some group G, you have some N, which is a normal subgroup in G. And what we do is we form a new group, G mod N. And what are the elements of this group? Well, what we do is we take the set of all G plus N for G in G. Let's dim that a little bit. There we go. So we take this and we have an operation. We say that G plus N times H plus N is equal to GH plus N. So for example, what would a nice example be? Well, maybe the simplest non-trivial example that I can give you is something like Z4. This way we can try modding out by a group of size 2 and still get something left that's not trivial. So in Z4, what is our set? It's 0, 1, 2, 3. What we could do is we can take the normal subgroup 0, 2. Note that this is closed under addition because if you add two evens, you get even. And we're mod 4. So that's going to work out just fine. So what we can do here is what we can have is we can have the sets of the form G plus N. So what would we get? Well, I'd get 0 plus N, which means the set of 0, 2. And 1 plus N is going to be the set of 1 plus 0 and 1 plus 2. And I get 2 plus N, which is going to be 2, 0. And I get 3 plus N, which is going to be 3, 1. And notice right off the bat that since these are sets, they're not ordered pairs, they're sets, these are equal and these are equal. So some things are going to be equal when we do this. And we want to be very careful that if we say have equal things, we get the same output if we multiply in our group. For example, let's say I have G plus N times H plus N and G plus N times J plus N. Now, if H plus N is equal to J plus N, even if H and J are different elements of the group, since H plus N equals J plus N, however I define my multiplication, I had better get the same thing out. Because if I multiply the same thing to G plus N, even though it might look different, I had better get the same output. Okay, now one thing I could do here is I could actually even make a multiplication table here, because I know 0 plus n and 2 plus n are one thing, and 1 plus n and 3 plus n are another. So what I could do is I could do a little thing like this, where I take 0 plus n, and 1 plus n, and 0 plus n, and 1 plus n. And I don't have to list 2 plus n because it's the same as 0 plus n. And I don't have to list 3 plus n because it's the same as 1 plus n. And if we do this out, and if you could do the computation yourself, you will get this, which as you see is its own group. It has an identity, which is 0 plus n. Every element has an inverse. 0 plus n has inverse 0 plus n. 1 plus n has inverse 1 plus n. And it is associative. You can confirm that. As a matter of fact, I mean, this is the same table up to isomorphism as Z2. You know this is associative, so therefore this must be associative. So this is the process of constructing a quotient group. So now what we want to do is we want to construct a quotient vector space. So what we're going to do is we're going to have a vector space and we're going to have a subspace. So let's, for a little example, just take, let's take V as R2, and let's let U be the set of XX for X in the rails. Or we could say lines with slope 1. There's a lot of different ways we could think about this. If we're thinking about it visually, we could say that, actually. Only if we're thinking about it visually. But we could also say the set of XY, so that y is equal to x. Lots of ways to write that set. Okay, so this is a picture of V. This is a picture of U. Not perfectly drawn, but okay. Okay, so what I want to do is I want to do the same type of thing that I do for groups. What I'd like to do is I'd like to take elements of the form V plus U, the set of all V plus U, where V is in V. And you'll notice that some things are going to be the same. For example, let's say I have 1, 0 plus U, and I have 2, 1 plus U. Well, what would 1, 0 plus U be like? Well, it would be the set of elements in U, every possible element in U, with 1, 0 added to each of these elements, right? This is a set of elements. It's not a single element, it's a set. So what would happen, I'd get a 1 added in the first coordinate. So what I might have is I might have 1, 0, that would be here. Or if the value of x was, say, 2, 2, I would have something like 3, 2. 3 here. Or if the value of x here I started off with was 1, when I add the 1, 0, I would get 2, 1. And as you see, what I'm going to get is I'm going to get a bunch of things as I'm plugging in points. I'm going to get a line right here. So this is equal to 1, 0 plus u. But it's also going to be equal to 2, 1 plus u. If you think about that, well, what happens when x is 0, 0? What do I get? I get 2, 1. Oh, I already have 2, 1. What happens when x is 1, 1 and I add 2, 1? Well, then I'm going to get 3, 2. Oh, I already have 3, 2. So I'm getting the same line, so this is going to be also 2, 1 plus u. So these two are equal. Those are equal to each other. So there's going to be many things equal to each other. And the important thing, if we're going to make this into some sort of a quotient vector space, is that with whatever operations I have, if I do something with the equal elements, I should get the same output. It shouldn't be determined by whether I use 1, 0 or 2, 1 if 1, 0 plus u is equal to 2, 1 plus u. Okay? So what I'm going to need to do is I'm going to need to define things in the right way. And we'll actually might as well just go out. So I'm going to define V mod U is going to be the set of all V plus U for V in V with two operations. It's going to be the quotient vector space. So we have a set. And now I'm going to have my two operations, which is going to be, let's see, I got to pick letters. I don't want to pick V and U because we're using them, so let's do W and X. So I'm going to do W plus U plus X plus U equals, well, I'm going to do what, hopefully this will work. I haven't shown that this will make any sense, but hopefully this is a simple way I could do it. And I'm going to do lambda times W plus U equals, oh, lambda W plus U. I'll put parentheses around that too. Why not? Okay, so I have my addition and I have my scalar multiplication. But the first thing I'm going to need to do is I'm going to need to show that these operations are well defined. That means if I have different things that are equal to x plus u, and they might look different because of the element here, but they're not actually different because the set is going to be the same. Like let's say I have x1 plus u is the same as x2 plus u, even though x1 and x2 might be different, just like these two numbers were different here. If I have two things that look different but are actually the same, I better get the same output, because I know that if I want things that, if I have things that are equal here, and I add, then I don't want to get randomness depending on which representative I chose. I want to get the same thing. As long as I'm adding the same thing, I should get the same thing out. So that's called being well defined. And what we need to do is we need to show these are well defined. So let's try that in the next video.